Hello everybody, and welcome to our next video here on thermodynamics. What we're going to finally do in this video is we're going to begin to put some numbers, or at least show you how we would put some numbers to evaluating numerically, quantifiably, this concept of entropy change, delta S. So we are going to finally quantify delta S. Now, in order to do that, what we're going to do is first talk a little bit about the second law of thermodynamics. Okay? Now, you probably remember the first law of thermodynamics, and that is that energy is conserved. It can't be created, it can't be destroyed. You know, you're not God, we can't be creating and destroying energy. So the first law of thermodynamics is that energy is conserved. The second law of thermodynamics has to do with this concept of entropy, which we now have hopefully developed as this idea of quantifying the numbers of ways you can arrange the object of study, be it positional entropy or classical entropy that we've talked about in the previous videos. So the second law of thermodynamics requires me to bring down this equation here. Now, there's some details missing here, so don't worry that it looks kind of silly right now. The second law of thermodynamics is going to tell us that the entropy change for the universe is going to be equal to the entropy change for the system plus the surroundings. That's really not the second law. The second law bit comes in when we talk about the delta S of the universe. And namely, the delta S of the universe is going to be positive anytime we have a spontaneous process. So you're looking at some chemical transformation. If it happens, it's spontaneous. Again, and we'll get to the details of this later on, maybe you needed a specific set of conditions to make it happen, but one way or another, some chemical transformation happens. That tells us it's spontaneous. And since it's spontaneous, that also tells us that the entropy change of the universe, the whole thing, has somehow gone up. Now, we're not going to be looking at the entropy changes of the universe per se. What we're really going to be looking at will be the entropy changes of the system, the thing we're studying, and then any change that that has on the surroundings. So we're going to, as we always do in thermodynamics, dissect the universe down into system and surroundings. And so in our first attempt to quantify entropy, I'm actually going to take a little bit of a physics approach. Right? When we talk about sign conventions, chemists do it correctly. We do our sign conventions with respect to the system. Physicists do it incorrectly. They do it with respect to the surroundings. Now, we're going to keep the chemistry sign conventions, but we're going to kind of do a little bit of a physics approach, and that we're going to first look at entropy change with respect to the surroundings. All right, so let me create a little bit of room here. And we're going to talk about evaluating, trying to quantify the delta S of the surroundings. Now, anytime we evaluate a change, be it a change in how much money you have or any other kind of quantifiable change, there's two parts that you have to evaluate to that change. The first part has to do with what the sign of the change is going to be. So we have to look at the sign. Is it positive or is it negative? And to understand the sign of the change in the entropy, we have to go back to heat. Now, the important thing to remember here is we're talking about the surroundings. Okay, this is delta S of the surroundings. Okay, so let's think about a reaction that is endothermic. So heat is going into the system. So if we have an endothermic system, that tells us that the delta H of the system, do you remember, from a chemistry perspective, if the system is gaining heat, the sign of the delta S of the system is positive. So that tells us that it's endothermic. Now, that heat that's going into the system must be coming from the surroundings. So that's going to imply for us that the change in the entropy of the surroundings, in this case, will then have to be negative. We talked about energy before. If the surroundings are losing energy, then that means that there are fewer ways to arrange that amount of energy in the surroundings, so its delta S would be going down. Conversely, if we have ourselves an exothermic reaction, so the delta H of the system is negative, heat's leaving the system and going into the surroundings, that tells us we're adding energy to the surroundings, so the delta S of the surroundings is going to have to be positive. So if I want to quantify the change in entropy of the surroundings, first part I have to do is the sign, and I can evaluate the sign of the entropy change by recognizing the heat exchange that's going on. Is heat coming into or going out of the system? Therefore, is it coming out of or into the surroundings? So that takes care of the sign of delta S. So let's move that over there. So that's all for the sign of delta S. Now let's talk about the magnitude of delta S. Okay, so just like any change, again, if we talked about, say, monetary change, you want to know if your balance is going up or down, then you also need to know by how much is it going up or down. So if we want to evaluate an entropy change, we've taken care of the sign, now we have to take care of the magnitude. And the way to think about this is, I'm going to give you a little bit of an analogy. Okay, let's talk about sound and really a sound disturbance. Imagine you're in a very quiet library, okay? What's a library, right? But you're in a very quiet space. Maybe it's a library. And the person next to you is starting to kind of scratch their nose, and they're going to develop a sneeze. And let's say it's a really loud sneeze. If that really loud sneeze happens in a quiet library, that's going to make a pretty noticeable disturbance, okay? The quietness, and then all of a sudden that loud sneeze. Now, conversely, let's say that person was going to do a sneeze in a really busy section of, say, New York City, maybe Times Square. And that person lets out that same rip-roaring sneeze. It's going to turn out that the amount of disturbance that that sneeze creates in the already loud environment of New York City isn't going to be nearly as much. So the change that that sneeze creates in a quiet library is actually bigger than the change that same loud sneeze might make in a busy part of New York City. So too with entropy changes and its magnitude. The magnitude of the entropy change is going to be proportional to the temperature in which the heat that we talked about in the sign portion is going into or coming out of. Most specifically, the change in the entropy, the delta S of the surroundings, will be proportional to the reciprocal of temperature. So if it's already hot and you dump more heat into it, that's not nearly as much of a change than if you had a cooler environment to which you then added heat. Goes back to the analogy with the sneeze and the quiet or loud environment. Now, hopefully I don't have to point out, but this temperature here, what scale are we going to be using? We're using Kelvin. Of course we're using Kelvin. All right, so now we have the two components that are associated with delta S. We've taken care of the sign bit over here, and now we've taken care of the magnitude bit. All right, so I'm going to clean up a little bit of space here. I need to move some things out of the way. So now I can quantify entropy change for the surroundings. So my delta S for the surroundings is going to be equal to the change in the heat for the system divided by the temperature. And we're going to assume that the system and the surroundings are at the same temperature. And then I also need to put a minus sign in front of that. Now, I'm going to take a little bit of extra time, and I'm going to go ahead and box this guy, because this is really our first quantifiable change that we've arrived at in this unit. So, let's think this through. If I have an exothermic reaction, that tells me then that the delta H of the system, okay, it's exothermic, the delta H is going to be negative. Delta H is negative. That negative sign there then makes the whole quantity positive. So for an exothermic reaction, the delta S of the surroundings would then become positive. And if it's being dumped, if that heat is being dumped into an already hot environment, the reciprocal temperature cuts down the amount of impact that heat exchange would ultimately have. All right, so we have here our first time that we've quantified an entropy change. Now, it's important to note that this entropy change really only works, this equation really only works for isothermal conditions, one temperature. Now it turns out there's a lot of changes in chemistry that happen at a constant temperature, so equations like this will actually be fairly useful for us in a lot of different circumstances. Now again, let me draw your attention, we're talking about the surroundings here. We're going to have a whole slew of ways of evaluating the entropy change for the system, and we're going to start taking care of those in some future videos. But here's our first example of quantifying an entropy change associated with heat exchange at a constant temperature.